In this section, we're going to be going over another differentiation rule called the chain rule. So let's say that we are asked to take the derivative of this function right here, f of x equals the square root of x squared plus 1. The formulas that we have so far for taking derivatives, power rule, product rule, quotient rule, that does not let us take the derivative of this function. So this is where the chain rule is going to come into play. So first, something that's very important is notice that the function f, that capital function f, is a composite function, which essentially means it's a function within another function. For example, if we let little f of x equal the square root of x and g of x equal x squared plus 1, then we can put these functions together using a composite function, f of g of x, and it would be taking g of x and plugging it into f of x. So it would be the square root of g of x, which is the square root of x squared plus 1. So that original function is a composite function. So the chain rule here is going to help us take derivatives of composite functions. So the chain rule states that if g is continuous at x and f is differentiable at g, then the composite function f of g of x is differentiable at x, and the derivative of that function is given by this right here. So capital F of x, the derivative of capital F, is going to be f prime of g of x times g prime of x. And if you want to take a look at it, I'm not even going to bother reading it off here in Leibniz notation. That's what it would be in Leibniz notation. The way that I'm going to be reading it is right down here. The derivative of the outer function, leave the inside alone, times the derivative of the inner function. So make sure you know both of those, the things that I highlighted here. Make sure you know the actual definition written out using that prime notation, and then I'm going to be reading it out in words. So let's do a bunch of examples here. Pretty much the rest of this section is examples. First thing you have to do is recognize, just like the other rules, when to use it. So once you see a function and you recognize it's a composite function, it's a function with inside another function, that's how you know you're going to be using chain rule. So this first example, we want to find d dx, the derivative of x squared plus 3x minus 2 raised to the 100th power. So first, before we do it, let's recognize, I'm going to show you two ways that you can kind of do it. So we can think of this function as its own function, h of x. I'm just going to rewrite it. We know it's a composite function. We can say that h of x equals f of g of x, where f of x is the outer function. The outer function here is something to the 100th power, so x to the 100th power. And then the inner function, g of x, is what's inside the parentheses, x squared plus 3x minus 2. So you kind of make sure that it works. Make sure that if you do f of g of x, you end up getting the original, which you do, because you would take g of x and plug it into x, making it x squared plus 3x minus 2 to the 100th. So if we wanted to do this using the definition that we wrote above, h prime would be the derivative of the outer, leave the inside alone, times the derivative of the inside function. So once we have these set up down here, it's pretty simple. So it's going to be f prime of g of x. So that's going to be, we know that f prime, the derivative of x to the 100, that's power rule. That's 100 times x to the 99th. But we're keeping g in there. So that's x squared plus 3x minus 2 times g prime of x. That's g prime, here's g. That's going to be 2x plus 3. So we could simplify this a little bit if you want, but there's your derivative of that function. So I don't like doing it that way. If you like doing it that way, that is completely fine. I'm going to go ahead and do it the way where you kind of read it out loud to yourself. So we recognize it's a function within a function. So we recognize that the 100th power is the outside, can be thought of as the outside function. So we need to use the power rule. We bring it out front. We leave the inside alone. Subtract 1 from the exponent. Multiply by the derivative of the inside. The derivative of x squared plus 3x minus 2 is 2x plus 3. So we can simplify this a little bit. All I'm going to do is distribute that 100 to the 2x plus 3, and I'm going to make it, actually I won't even bother doing that. I'm just going to leave it as 100, and I'm just going to rewrite the order. 100 times 2x plus 3 times x squared plus 3x minus 2 to the 99th power. Okay, so let's do a couple more examples here. Let's do the example that we started with. We have capital F prime. We want to find capital F prime if f equals the square root of x squared plus 1. So before we do anything, let's recognize that we can rewrite this as x squared plus 1 to the 1/2, right? The square root is the same thing as a 1/2 exponent. So now we recognize it's pretty similar to what we just did. We have a function within a function. We have this outer function of the square root, the inner function of x squared plus 1. So we want the derivative, f prime of x. It's going to be the derivative of the outer. Power rule, it's the general version of a power rule. We bring that the 1/2 out front, leave the inside alone, subtract 1 from the exponent, times the derivative of the inside. The derivative of x squared plus 1 is 2x. So same idea as before, and if we simplify this, the 2's actually cancel, right? 1/2 and the 2, and we're left with x over the square root of x squared plus 1. And the reason why I wrote square root of x squared plus 1 in the denominator is because we have x plus 1 to the negative 1/2. We make it a positive exponent by putting it in the denominator, and the 1/2 power is the square root. So it's x over the square root of x squared plus 1. Okay, and let's keep on going. Let's differentiate the following. Let's see the difference between these two. First one is y equals sine squared of x. So hopefully we remember that what this actually means is sine of x all squared. We just like to use this notation so we don't have to use parentheses. It looks a little bit cleaner. So now hopefully we also see that this is going to be chain rule. We have a function within a function. We're going to be doing that power rule first again, bringing the 2 out front. We leave the inside alone, subtract 1 from the exponent, times the derivative of the inside. The derivative of sine is cosine. So we get 2 sine of x times cosine of x. And let me just label this as y prime. Forgot to put y prime there. And that's it for that one. Let's see how it differs from the second one. So the next one is y equals sine of x squared. So take a look at how these two are different. So this time our outer function is the trig function sine, and the inner function is x squared. So y prime is going to be the derivative of the outer function. The derivative of sine is cosine. Leave the inside alone, times the derivative of the inner function. Derivative of the inner function, the derivative of x squared is 2x. So just going to rewrite it as 2x times cosine x squared, and that is the derivative for that function. Okay, a couple more examples. We want to differentiate y, which is 1 over the cube root of x squared plus x plus 1. Let's go ahead and rewrite this. We know this is the same as 1 over the cube root is an exponent of 1/3. Let's go ahead and put this in the numerator. It'll go in the numerator because it'll end up as x squared plus x plus 1 to the negative 1/3. So negative exponent reciprocates it, so now it's in the numerator. So now it's going to be a little bit easier because now we can recognize that that's just going to be chain rule again. We're going to do that general power rule, bring the negative 1/3 out front, derivative of the outside, leave the inside alone. So we still need to subtract 1 from that exponent. Negative 1/3 minus 1 is negative 4/3 times the derivative of the inside. The derivative of x squared plus x plus 1 is 2x plus 1. And maybe let's just clean this up a little bit. That's going to end up being 2x plus 1 is the only thing left in the numerator. We have the negative still out front. That denominator is going to be 3 times x squared plus x plus 1 to the positive 4/3. Okay, so that is that derivative. And we could have just left it like this right here, but I like to clean it up if I can. But whatever you prefer is fine. Next one, let's find the derivative of g of t, where g of t is t minus 2 over 2t plus 1, all to the 9th power. So hopefully you're kind of getting a hang of some of the patterns for this. A lot of the time, obviously not all the time, but you're going to be using that power rule a lot for these questions first. This one is no different. It's going to be power rule first, derivative of the outside. We leave the inside alone, subtract 1 from the exponent, times the derivative of the inside. So now we actually need quotient rule for the derivative of the inside. So let's do this without making it too messy. It's going to be low d high, the derivative of the numerator, t minus 2 is just 1, minus high d low, the derivative of the denominator is 2, all over low squared. And let's go ahead and just rewrite this. So you can see that you definitely are going to be typically going to be using multiple rules in one for these more complicated questions. So we have, I was going to rewrite the first part, 9t minus 2 over 2t plus 1 to the 8th. Let's simplify this fraction over here on the right. We're going to have, let's just distribute this 2 first. Actually, let's just do that in one step. If we distributed, essentially we'd be distributing a negative 2. So this would actually end up canceling. I'll just do it on the side so I don't have to rewrite this all. That whole numerator would be 2t plus 1 minus 2t plus 4. The 2t's cancel. We end up getting 1 plus 4, so 5. So that whole entire numerator is just 5 over 2t plus 1 squared. And maybe just simplify this a little bit so it looks a little nicer. We have 9 times 5, so we get 45. In the numerator, I'm going to split up that fraction and write it as t minus 2 to the 8th. So that denominator would be 2t plus 1 to the 8th. The reason why I split it up is because now we have 8 of these ones. We have 2 of these ones. They combine to 10, right? We multiply common bases, we add the exponents, so we have 2t plus 1 to the 10th in the denominator. Okay, and let's keep on going. We want to differentiate y equals 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. So first, notice that we have these two main factors now. So this is going to be product rule first. So it's product rule first. So it's going to be the first one times the derivative of the second one. The derivative of the second one, we need chain rule. So it's going to be 4, leave the inside alone, times the derivative of the inside. The derivative of x cubed minus x plus 1 is 3x squared minus 1. So that whole thing was first times the derivative of the second plus the second times the derivative of the first. The derivative of the first one is derivative of the outside, leave the inside alone, and times the derivative of the inside. So the derivative of 2x plus 1 is 2. Okay, so excuse me. So now we have to simplify this a little bit. And what I'm actually going to do here is I'm going to factor out a greatest common factor. We have these two big terms, and let's go one at a time here. So let's look at the numbers, the coefficients. We have a 4 and a 5 times 2. The GCF from those two would be a 2. Next, let's take a look at the 2x plus 1 portion. So if you're factoring 2x plus 1 out, you're going to factor the one with the smallest exponent, which is to the 4th. Next, let's take a look at the x cubed minus x plus 1. Take the one with the smallest exponent out, which is a 3. And it looks like that's our only GCF. And now let's think about what we have left over. So from the first one, we'd have left over a 2, because 4 divided by 2. We'd have 2x plus 1 to the first, and we would have the 3x squared minus 1. And that's it from that one. So now for the second portion, we would have one of these x cubed minus x plus 1s. We would have, actually we'd have this 5 still. I'm going to put the 5 out front. And we would have, I think that's it. Yep, so that is it. Close those parentheses. And for the last thing, I'm not going to write the whole thing out again, but all I'm going to do is simplify what's inside that last batch of parentheses. And so I'm simplifying this whole thing. We would have to do some foiling, combining like terms. We should end up getting 17x cubed plus 6x squared minus 9x plus 3. So if you can simplify it, it's usually better to simplify it. It just looks a little bit cleaner. All right, let's keep on going here. We have to differentiate y equals e to the sine x. So these are pretty common to see, where you have e raised up to some function and we're taking the derivative of it. So the outer function here is e to the x, essentially. The outer function is e raised up to just an x. So it's going to be the derivative of the outside, which is, it's the same, right? Because we know the derivative of e to the x is just e to the x. So the derivative of the outside, leave the inside alone, times the derivative of the inside being sine of x. The derivative of sine of x is cosine of x. So this is going to be cosine of x times e to the sine of x. So the kind of the shortcut way to think about differentiating e raised up to a function is that it would end up being something like this. Like if you have the derivative of e to f of x, whatever f of x is, that's going to be e to the f of x. So that's the derivative of the outer function, which remains the same, times the derivative of the inner function, so f, whatever f prime is. In this case, f prime was cosine of x. Okay, so that's just kind of like a little tip for differentiating something in that form. Okay, let's make one that looks a little bit crazier. We want to find f prime for f of x equals sine of cosine of tangent of x. So this one might go a little bit slower here. Okay, so it's definitely going to be chain rule, right? We have a couple different functions within functions. Hopefully we agree that sine is the outer function. So it's going to be the derivative of the the derivative of the outer function, leave the inside alone. So the derivative of the outer function is the derivative of sine. which is cosine. We left the inside alone, which means we just rewrite it, times the derivative of the inner function. So times, this is why I said I'm going to go a little bit slower, the derivative of the inner function. So I'm just going to write it as d dx, the derivative of that inner function. So this is our derivative, but we still have to evaluate this right here. So that's going to actually be chain rule again. So we're going to get the first part just rewritten, cosine of tangent of x times the derivative of this portion right here. So that's chain rule. It's going to be the derivative of the outer function, which is the derivative of cosine, which is negative sine. Leave the inside alone, times the derivative of the inner. The derivative of tangent is secant squared. Okay, so that is technically our answer. Let's clean this up a little bit if we even can. So there's a negative, so let's just put the negative out front. And maybe let's, it doesn't really matter too much which order we write this in. Let's just leave it in that same order. Cosine of tangent x times sine of tangent x times secant squared x. Okay, so kind of looks messy for that one. So that one was chain rule twice. So basically we have one more example before we get into like the last one small page. We want to differentiate y equals e to the secant of 3 theta. Okay, so let's go ahead and maybe we know it's going to be chain rule, we have a function within a function. Let's use that little kind of shortcut that we had for differentiating e raised up to a function, which is it's going to equal e to the function times the derivative of that function. So let's go ahead and write that out. Y prime is going to be e raised up to the secant 3 theta times, I'm going to write it like this. It's going to be not d dx, but d d theta. d d theta of secant 3 theta. So let's go ahead and actually evaluate what the derivative of secant 3 theta is. That's going to be chain rule. So that's going to be chain rule because we have this function within a function. The 3 theta is within the secant. So it's going to be derivative of the outer. The derivative of the outer is the derivative of secant. The derivative of secant is secant times tangent. So the derivative of secant 3 theta is secant 3 theta times tangent 3 theta times the derivative of the inner, which is the derivative of 3 theta. Okay, so a little confusing here. So it's the derivative of the outer. Leave the inside alone. Derivative of the outer is secant times tangent. We left the inside alone, which was the 3 theta, times the derivative of the inner. The derivative of 3 theta is obviously just going to be 3. And sorry, I should have wrote this as d d theta. Okay, and now the derivative of 3 theta we just said is 3. So this is going to be 3 times e to the secant 3 theta times secant 3 theta times tangent 3 theta. So don't let the fact that they look kind of messy throw you off. Just make sure you stick to your rules and you should be good. So let's do one more thing here, and that's going to be using the chain rule to differentiate an exponential. The exponential being y equals b to the x. So b here is the base, and it's going to be a number, and the x's obviously are variable. So we mentioned this, we touched on it several chapters ago, but we didn't have an exact definition yet. Now we're going to have an exact definition. And if we're differentiating b to the x, the derivative of b to the x is going to equal b to the x times the ln of b. So typically we're just going to leave it as the ln of b, like the ln of 2, the ln of 3, whatever it is. But that is the derivative for it. So we can see here that if we were differentiating d dx of e to the x using this rule that equals e to the x times the ln of e, we know the ln of e equals 1, so the derivative of e to the x is just e to the x. Okay, so let's go ahead and show why this is real quick before we see an example. Let's differentiate y equals b to the x using the fact that we can rewrite b to the x as e to the ln of b all to the x. Okay, so we would have d dx of b to the x, which we just said that is the same as d dx of e to the ln of b to the x. So we know that's the same, right? Because e to the x and ln of x are inverses, so we can think of them as crossing each other off and canceling each other off when they're taken as inputs to another, which would just leave us back with b to the x that we have there. Okay, so we can go another step further here, and we can say that if we have a power to another power, we can combine them by multiplying them. So we can combine those as e to the ln of b times x. Let me throw parentheses around that so it looks a little cleaner. So e to the ln of b times x, power to a power, combine them by multiplying it. And now this is when we can use, it doesn't look like it's any easier, but it actually is. This is when we can use the rule, that shortcut rule, where we have the derivative of e to a function. That's going to equal e to the function times the derivative of that function. So all we're going to use is that little rule right here, and that's going to take us to our answer essentially. So that's going to be rewriting it, e to our function ln of b times x times the derivative of that exponent function. So that's going to be d dx of the ln of b times x. So we have e to the ln of b times x times, so the derivative of ln of b times x is actually easier than it looks. Ln of b is just a number, right? So if we were taking the derivative of 2x, we know the answer is 2. If we were taking the derivative of 3x, we know the answer is 3. So no matter what that constant is, that's going to be the derivative. Ln of b is just the constant, so the derivative of ln of b times x is just ln of b. And the last thing is now we can use that inverse property and say that those e to the ln of b to the x is going to end up, the e and the ln cancel because they're inverses, and we're just left with b to the x times the ln of b. So that is what we were trying to prove. We were just trying to prove this definition up here. So take a second and maybe try to do it on your own. It looks a little confusing because we have a lot of letters floating everywhere, but just try to understand that, just so you know why that is. Okay, let's do one example here. We want the derivative of y equals 2 to the x. So based on the rule that we just learned, we know that y prime is going to be 2 to the x times the ln of 2. Pretty straightforward if you know the rule, which we just showed up here. The b in this case is 2. Okay, so that is chain rule. That's another differentiation formula. You have to recognize it's a composite function, and then do the derivative of the outside, leave the inside alone, times the derivative of the inside. Okay, so that is it for this chapter.